Welcome everyone! In this demo we'll explore a simulated scenario in which a roadside unit, or RSU, detects a parked vehicle and broadcasts its presence to a connected and automated vehicle running Autoware, helping it avoid a potential collision. This is achieved by transmitting a Collective Perception Message, or CPM, the ETSI V2X standard for sharing sensor detections among vehicles and between vehicles and roadside infrastructure. In this scenario, the parked vehicle is a ghost object that does not physically exist on the road. As a result, it cannot be detected by the vehicle's onboard sensors. However, it is intentionally reported by the RSU to illustrate the potential of V2X-enabled collective perception to extend a vehicle's awareness beyond the range of its own sensors. The received V2X messages are processed by Autoware through a custom module developed as part of this work called the Dummy Object Injector, which injects the shared detected objects into the vehicle's perception pipeline. First, let's place the ego vehicle and set a goal pose. Right now, Autoware's own multi-object tracker, the module responsible for tracking detected objects over time, is showing an empty list of objects, and the Dummy Object Injector module hasn't published any message yet. This implies the car's onboard sensors haven't detected anything, and the injector module is either not running or hasn't received any messages. As a result, RViz, the visualizer, shows no detected objects, and the vehicle will follow the predefined route without any issues. Now, we launch the Dummy Object Injector node. As you can see, it's listening on the input CPM topic, as defined in the launch file, and a test script that continuously publishes standard CPMs with a list of objects. Unlike standard Autoware dummy objects, which simulate a local sensor detecting a fake target, this node is actively receiving standard ETSI CPMs in ROS2 format, processing them and sending the perceived objects straight into Autoware's tracking pipeline. Both topics are now populated with the object defined in the script, as it's being continuously published. This is what the object looks like once it's published by the tracker. In RViz, we can see our vehicle has already changed its path to avoid the newly detected parked car. Let's set it to auto and see how the situation is handled. Up until now, the test script has only been publishing a single static object. By enabling a second object in the script, this one with a non-zero velocity value, we can see how Autoware handles dynamic V2X targets. Once we include it, we can see that Autoware accepts it as a valid detection and immediately tries to predict its future trajectory, even though the object itself isn't following the road. When the node receives a CPM, it uses dead reckoning to estimate each object's position at the message's reference time using its reported velocity and measurement delta. This is necessary because unlike CPMs, which carry both a global reference time and a per-object measurement delta, the output message the tracker expects only contains a single timestamp. This module runs alongside the vehicle's onboard sensors, feeding perceived objects directly into Autoware's multi-object tracker so they can be fused together. For this demo, we're using a test script to publish CPMs in ROS2 format, simulating what would normally come from an RSU or external V2X transceiver. Note that the module requires a valid map to be loaded. It relies on the map projector topic to convert global reference coordinates into local frame positions, so without map information, the conversion will fail. And that's all I have to show today. Thanks for watching.